So we define the function that calculate the difference between theoretical bond price and observed bond price and squared it. And we want to make it 0. So let's start from the small tree, t equals 2. And then we have this small tree, and then this is the theoretical bond price. It is now confusing, so let me close this one. Yes, theoretical bond price, this one, and observed bond prices, of course, print A. And then there is a gap, theoretical bond price and observed bond price, and then our M old is 0, and then our mu is here, mu is this one 0.003. So if we put 0.003 M old 0, then it becomes this 2, and then calculate the error, then of course we have this one, which is this one minus this one and square term. And we want to make it 0 by finding appropriate this one. So let's try code. So where do we start it? Here, first, what we can do is parameters. Let's move this one. Let's write down this one again over here. And then let me check whether we have minimization one, which is this one. So let's move on over here. We don't have to do that, but not to forget it. Okay. And then, well, we want to minimize it, temp, okay, and the minimize function is bond error. And then our initial guess is, let's make it the most least value, M world minus 1. So here it is clearly 0. And argument that we pass through is in the bond error function is A param M world. So A params M world. And of course, I want a method. Method is my favorite method, minimizer method, L pf gs.b. And then if we print trim temp, and this is solution. So actually this is the optimal drift term, not 0.3. So let's just print out this part, which is this one. And then let me copy this one, copy, and let's make initial guess over here. Because this guess is correct, this one should be 0, right? So this is practically 0. So our initial guess is correct. But we don't want to stop here. What we want to do is actually we want, so let me put over here. And what we want to do is actually we want to make t equal 3, and we want to make drift term as fine caliber drift term that matches 9 months bond as well, which is this one. This is theoretical bond price and observed bond price, and about the difference of the difference is now this one. We want to make now this part 0. I updated M old, and then we will find this one. So instead of this one, let me put M old minus 1, most least one. Okay, same. And we want to make it 0. So here, what we have to is we have to find roof. So t equal to, well, yeah, let's make it t equal to. And then for I in range 0 t, and then temp minimize this one. And then when we estimate M old and we want to update this one, M old add, and then basically we add this one, which is the new drift term over here. Then we updated it, and then we want to run the tree again. I want to see the tree. Actually, this is, I think it is enough. M old tree, M old add is not defined. Okay, sorry. Dot, and then print M old. And then, yeah, this is first one, and based on that, this is second one. So if I copy this one, let me see whether it becomes 0. Over here. Then indeed, we have almost 0. So our answer is correct. So, well, let's also print out because we calibrate M, so we can correctly, uh, we using this draft system, now we know what is the correct interest rate tree and what is correct bond tree. Inconsistent, that is consistent with this drift sum. So print R tree, and then first one is mu, so M old, of course, and then R0 volatility and DT. Okay, and then we can actually tabulate it to make it pretty. Yes, so we have interest when this one matches this one, there is no drift term. So for this drift term, we have interest rate that is consistent with this drift term. And then next step for this one, we have bond, we have movement of interest rate that is consistent with this part. Let's also see the corresponding bond price. Okay, bond tree here. Well, I can move this one here. Let's make it name is R3 temp, and then print out this one over. Oh, sorry. Yeah, and then print out this one, and then this one and DT. Then here now we have drift term, we have interest rate, and we have bond tree, and then we have extended one, another interest rate. Now we have 6 months term. So it is evolution of a 6 months bond, and it is the evolution of 9 months model. So basically we are done. We finished calibrating Holy model. So this is the end of Holy model. Okay. Because we estimated it, let's do more exercise, some more practice, because it's very small, small tree. So let's make it larger tree. Let's try a larger tree. For example, what can you do? For larger tree, let me generate random number and the random seed. Let's set up the seed so that you can have the exactly same answer with mine. And then let's generate a series of interest rate. So RS is spot rate, NP random. How many? 10. Okay. 10 would be, yes, I think 10 trees would be fine. 10 data. And then, yeah, let's make 10 and then divide by 10. Okay, LRS. So suppose we have this data. This is also random spot rate. So they are random spot rate. And then about DT. Now, time step is of course, because we have 10, so MP range 111, right? And then we multiply T. So we have a time step. Yeah. So this is the 3 months, 6 months, 9 months, 1 year, and blah, blah, blah. So this is time. So given this time now, we can generate, I think we can generate a bond, okay? We can generate a bond so that we can generate bond prices, bond, A bond, okay? This is the 100, face value is always 100, and exponential of minus RS multiplied by TS, which is error, multiplied NP. Only one size array can be converted to Python scalar. Okay. Let me divide it. Only one size array. So instead of divide it, what I can do is 100 NP non-pi. Okay. And then A bond. This is our bond price now. So in the previous case, we have only 2 bonds, right? We have only 2 bonds. Now we have 8 bonds. So we can, given this 8 bond, we can generate a larger trees for Huanli model, which we can do right now. So to make it simple, let's make a small tree. Let's start from small tree. Let's say t equal 3. And then initial value, m old. Okay, m old. This one, let me copy this one. Okay. Actually, not only copy this one, we can also copy, I think, this one. Okay. Let me see whether there's no problem of copying this one. Okay, so now we have bond 2, 3, 2, 3. Okay, bond error m old params m old method. Yes, this is not A, right? This is A bond. Well, so now we have a larger bond, right? So, well, 3, that seems pretty good. So if we increase this one as 5, now we have, well, we have this larger right Huanli tree, right? This is for 3, 6, 9, 1 year, so 1.5 year of interest pass and price of bond consistent with that. Okay, long-term bond prices. Okay, let me make it t equal 10. Wow, so we have this huge bond. So I think this is the end of Hohenli model. One possible homework for students is to make one possible homework for student is to modify, it in code slightly, and then generate develop code for black dom and toy model, which would be good practice. So here, possible homework would be to modify the code above code for to develop BDT model. Okay. Instead this delete this part text. Okay. Yeah. Possible homework would be to a possible homework. A possible homework would be to modify the above code to develop black dom and toy model. That would be a good exercise. Thank you.